Alright, so this is we're going to start talking about Faraday's law and magnetic induction. So the first thing to point out when we talk about magnetic induction and Faraday's law is we need to define a term called magnetic flux. So kind of one of the cool things I think about when we talk about magnetic induction is that a current, moving charged particles, creates a magnetic field. Well, it happens to work out, and we'll find this here in this lesson, that a changing magnetic field can create a current in a loop of wires. So the way I define magnetic flux is really exactly the same way that I define electric flux, B dot A. And so basically magnetic field strength multiplied by the area vector, which is the length of the area in a direction perpendicular to your loop or your surface. And so the way we'd write this as B A cosine of theta. If we have a closed surface, we might choose to write it as B dot dA. Now, what's true about changes in magnetic flux is that they induce an EMF on a conducting loop of wire. What an EMF essentially is a voltage. The term EMF really stands for electromotive force. I don't really like the term force because it's really talking about a potential difference, that it moves the charged particles around in that loop of wires. And what's true about that EMF is that it's equal to negative the change in flux as time changes. Now, you might look at that function and say, well, negative, that seems kind of odd. But we'll look here and we'll see why that negative is in there in a few seconds. Now, there must be three ways you could change the magnetic flux. The first way is to change the strength of the magnetic field. If you increased or decreased the magnetic field, you'd increase or decrease the flux. The second way is to change the area of your wires or coil of wires or loop of wires that's in the magnetic field. So increasing or decreasing that area, moving it into or out of the magnetic field. Those would be ways to change the area of your loop of wires that is within a magnetic field. And the third thing is to change how the loop of wires is oriented with respect to the magnetic field. So change this angle of the direction of the magnetic field with respect to the area of the coils of wire. Good example of what to do here is rotate the wires inside of a magnetic field. Happens to work out that most types of electrical power generation, it's that last thing, that third way that's actually happening. Now, where does this negative sign come from? What this negative sign really is doing is it's a way of mathematically showing what we call Lenz's law. What Lenz's law does is it determines the direction of induced EMF and induced current in a coil of wires due to a change in magnetic flux. A basic summary is that a current will be induced in a loop of wires that counters the change in flux. So if you're changing the flux in a way that decreases the magnetic flux, a current will be induced in the wires to try to maintain a constant flux through the middle. So in a way to produce a magnetic field in the direction of the current magnetic field. If you have a negative or a decrease or an increase in magnetic flux, the current would be induced in a way to try to decrease the amount of magnetic field going through the wires. So that negative sign really talks about that the EMF and current produced will try to create a magnetic field that does the opposite of what you're doing to magnetic flux as it is. So let's do a couple quick conceptual examples with Lenz's law and kind of talk about what this means. Here we have magnetic field coming out of the page at us. And so let's say we decrease the amount of magnetic field. What happens is the magnetic flux decreases. Because magnetic flux is B times A times cosine of theta. Well, I didn't change theta or A, but I did decrease B. What this means is that EMF and current induced will be in a direction to create a magnetic field that goes out of the page. Now, the direction of magnetic field that goes out of the page would be in this direction, the counterclockwise direction. You can use the right-hand rule to show that. Your fingers curl in the loop or in the direction of current around the loop of wire. Your thumb points in the direction of the magnetic field. Now, if we do the exact opposite to this situation, increase the magnetic field, this means that the flux increases, and so EMF and current induced will be in a direction to create a magnetic field into the page, opposite of the direction of changing flux. What this would be is a clockwise current going around this loop of wire using the right-hand rule. So let's take my circular loop of wire and say that it has a radius of 1.5 meters, and I'm going to place it in a magnetic field with an initial strength of 0.5 Tesla. I'm going to take the magnetic field and decrease its strength to 0 at a constant rate over a time period of 150 milliseconds. And I want you to calculate the induced EMF in the loop of wire, so what's the induced voltage, and what is the direction of the induced current. So first thing, we could do the direction of the induced current pretty easily. We'll save that for later, but let's calculate the induced EMF. Remember that EMF is negative change in flux. Well, flux is B dot A, or B times A. And so if you actually were to take and differentiate negative dBA over dt, you'd have to use the chain rule on that. So you get negative dB times A plus B times dA dt. Well, dA dt is 0. We're not changing the current or the area at all. So really, this is going to be change in magnetic field, or the rate of change in magnetic field times the area of your wire. We can find the area of the wire, pi r squared. We can also find the constant rate of change, that if it went from 0.5 teslas to 0 in 150 milliseconds, that means your change in wire is 3.33 Tesla per second. So if we multiply those two together, I get an EMF of 23.6 volts. I've dropped the negative sign here because I'm really just looking for magnitude. And what the negative sign really tells me is that this needs to be a counterclockwise current, or a counterclockwise flux. That the EMF and the current produced have to be in a direction that tries to increase the magnetic field through the middle of the loop of wire. So let's take a second problem, and let's take a U-shaped loop of wire that's inside of a magnetic field that's a constant 2 teslas into the page. And let's say this U-shaped wire has a metal rod that goes across it to form a complete loop of wire. And so I'm going to take this metal rod and pull it to the right at 1.5 meters per second at constant speed. It tells me that the metal rod has a resistance of 2 ohms and is 3 meters long, and we're going to assume the wire has essentially no resistance compared to that 2 ohms. So what I want to do is calculate the magnitude and direction of current within this metal rod, this blue piece, as I pull it to the right. So the first thing I know is the length of this side is 3 meters. So we could say EMF is equal to negative change in flux divided by time. And in this case, the magnetic field's not changing, but the area is changing. We could go one step further and say that the area is changing because we're pulling this thing to the right. If I define the distance left to right of this loop here as x, really what's changing is v dx dt, x is getting bigger. L remains constant in this case. So really, if we look at what this is, negative v, which is 2, L times v, because v is dx dt. So we plug all that in, we find, oh, the EMF is 9 volts. Now, if I know the EMF is 9 volts, I can figure out the current pretty easily, since V equals IR. I know R was 2 ohms, so my current is 4.5 amps. Now, in order to do the direction, I would do my right-hand rule, increasing flux into the page, which means I have to induce a current that creates a magnetic field that goes out of the page, which is, oh, guess what? The counterclockwise direction again. So it's going to go up through this rod of wire. Now the third problem that I have is I have a loop of wire that has area A and is placed in a magnetic field strength of B. And the loop is going to be rotated around, and we're going to rotate it at a constant angular velocity of omega. And what I want you to do is determine a function for the EMF induced in the loop of wire in terms of A, the area of the wire, B, the magnetic field, omega, that constant angular velocity, and theta, the angle that the wire is currently oriented at. So here we have this expression, and what magnetic flux really is B times A times cosine of theta. In the previous two examples, the area vector and the magnetic field were in the same direction. In this case, for most instances, that's not going to be true. Now, if I go and take and do the chain rule to B times A times cosine of theta, I really have dB dt A cosine of theta plus B dA dt cosine of theta plus B A d cosine of theta dt, which is what I have here. The first two of those terms are 0 because I'm not changing the area, I'm not changing the magnetic field. Well, if I take the cosine of theta and take its derivative, you get negative sine d theta dt. Well, d theta dt is also the angular velocity, omega. And so what you end up with is this function b times a times omega times sine of theta is the current EMF induced in the wire. What this would suggest is that you get a sine wave in terms of EMF. It would also suggest you get a sine wave in terms of current. The type of current you're actually producing here in this situation is alternating current, not direct current. That your current will vary based upon what this angle is. So let's give a quick overview of Faraday's law and Lenz's law and a couple of quick examples of some situations where those come up or where we would use those rules to begin to predict EMF and induced current.